Alrighty. Good morning. Hope everybody's doing fantastic. We are getting into probably our last unit, or I'm sorry, our last lesson for Unit 2B, and that is talking about indeterminate forms and a new rule called L'Hopital's. So this is just something extra we need to learn. We need to throw into this unit, and this is actually kind of taking it back a ways. It's kind of taking it back to evaluating limits. um, this involves limits and derivatives, and uses derivatives to help us evaluate limits that we might not have been able to evaluate in the past. So if we're taking it back to maybe Unit 1, we have a whole list of ways to evaluate limits going all the way down through squeeze theorem. This would be another way to evaluate a limit. And it turns out in calculus that this method shows up a lot because it is utilizing derivatives, something we learn in calculus, to evaluate a limit. All right. So before we jump into the actual method of L'Hopital's, we are going to refresh ourselves, or maybe even learn what an indeterminate form actually means. So, think about it. F of x is indeterminate if, when we evaluate the limit, we obtain the following. If we get 0 over 0, or infinity over infinity, and that could be positive infinity over positive infinity, or negative infinity over negative infinity, any type of infinity over infinity. If we get infinity times 0, or infinity minus infinity, another one that's actually considered indefinite is if you have 0, or indeterminate, is if you have 0 raised to the 0 power. So all of those are considered to be an indeterminate form, meaning that if we evaluate a limit and we get those answers, it doesn't necessarily mean the limit equals that. It just means we can't determine it while it's in that form. Okay. The ones that we see most often are 0 over 0 or infinity over infinity. Those are the most common indeterminate forms. And some would say, well, isn't that just 1 because you're doing the same thing divided by the same thing? Unfortunately, in those concepts, that's not necessarily true. You can't divide by 0 for 0 over 0. And infinity over infinity is not like doing a number divided by a number. Infinity is more of a concept, so you can't really just say that's equal to 1. Like, here's an example, for instance. I'm saying the limit as x is approaching infinity of e to the x over x squared. Well, we know what, so like when I'm taking the limit to infinity, if we consider the top function and the bottom function separately, e to the x, e to the infinite power is getting, think of the parent function as getting infinitely bigger. Okay, so this is actually going to reach infinity on top. And same thing for x squared. You think of x squared going on to infinity, it is also getting infinitely bigger. So this is infinity over infinity. Now, that would be considered an indeterminate form. We don't know what it's reaching based off of just plugging in infinity and thinking about end behavior. We have to do an extra step. And if we ever reach indeterminate form, then we can apply L'Hopital's rule. And that's what the next slide is going to be going over. All right. So with L'Hopital's rule, unless you're doing the form 0 to the 0th power, and that's kind of a special indeterminate form, I will say this, that something to consider is it must be a limit where you're dividing, and if it's not, you got to make it dividing. And again, we'll talk about how that works later on. But if two things are multiplying, you can bring one to the bottom by maybe making a negative power. But it's got to be in the form where something is divided by something. Okay. L'Hopital's is actually a pretty interesting concept, and it's not too terrible if we are good at taking derivatives. It says, suppose f and g are differentiable. Okay, so we have the f function and g function are both differentiable. And it's just specifying that g prime of x does not equal 0 because g is the one that's going to be on the denominator. And suppose that, all right, so the limit of x of f of x equals 0 and the limit of g of x equals 0, or that f's limit is positive or negative infinity and g's limit is positive infinity, then this is, oops, what are you doing now? This is L'Hopital's rule. What this is stating, okay, what this is simply stating, and this first part is kind of this first part is describing indeterminate form. It's saying that, hey, if we get 0 divided by 0, or if we get infinity divided by infinity, then this following is true. If I'm taking the limit of f divided by g, if I do the derivative of the top and divide it by the derivative of the bottom, then that limit is equivalent to the limit I'm starting with. Okay? And it actually simplifies down the process. It actually makes it so we can solve those indeterminate limits. Now, something I really want to specify here is this right here. This is not the quotient rule. All right? I'm not saying we take the fraction as a whole and do the quotient rule. I'm saying we take the derivative of the top and divide it by the derivative of the bottom, and that ratio, that limit, is going to be the same as the limit that I started with. Okay, they're equivalent by L'Hopital's rule. Now, there's some very specific wording and specific ways that L'Hopital is done correctly, and I'm going to explain that very thoroughly in our examples and in the following notes, because this question is asked almost every AP exam in some form to evaluate some limit doing L'Hopital's, and they count, and they're very strict with how they grade it. So I want to make sure we're very clear on how this works. All right, here's the steps. And I encourage you to pause the video and write these down as I'm, or just write them as I'm writing it. But this is kind of like the process behind this. Number one, you got to show the indeterminate form, which is the main ones are either 0 divided by 0 or some type of infinity divided by some type of infinity, plus or minus infinity divided by plus or minus infinity. But this is something that they've changed with how they grade this. Normally, in the past, they would accept you showing this or this, but now you have to write it a very specific way. It's okay if you're in your scratch work, you get to this point right here, like where you show 0 divided by 0 or infinity divided by infinity, but technically that is not written correctly. You have to explain it as the limit of the top and bottom separately. You have to say the limit as x is approaching a or whatever it is of f of x, for example, equals, it'll say 0, and you have to talk about the bottom of the function, which we'll call g of x. You have to say that it also equals 0. Like, you have to show the limits separately. Okay, so if you're starting off with the limit as x is approaching a of f of x over g of x, you have to explain in the indeterminate form by this process. You have to separate the limits and say, hey, the limit of the top equals 0, the limit of the bottom equals 0, and then that is enough information to determine that we're in indeterminate form. So then the next step you're going to do is you're going to say, okay, then by L'Hopital's rule, you have to state the name and you have to write it. You have to say by L'Hopital's rule, and then you got to write pretty much you got to write the rule. You got to write the rule out. You got to say, well, then by L'Hopital's, that means that what I'm starting with, I know is going to equal this. X approaches a of f prime of x divided by g prime of x. And then you solve that limit. Okay, then you solve that limit. Now, sometimes if you try to solve that limit, it's going to be indeterminate form again. And then we have to start the whole process over. We keep repeating steps 1 to 2 as many times as needed if you keep getting indeterminate form. And sometimes it might take 2 or 3 times, but eventually you'd get to the correct answer. All right. All right, let's look at a few examples, see how many we can get in under 30 minutes. All right. So, let us evaluate this limit by first plugging in pi over 2. So what we got is cosine of pi over 2 quantity squared all over sine of pi over 2 minus 1, which equals cosine of pi over 2 is 0, so that's 0 squared is 0, over sine squared, or sine of pi over 2 minus 1 is 1 minus 1, which is 0. Okay, so if I try to evaluate this limit, I get 0 over 0, which is indeterminate form. Now, if I ever get this point right here, sometimes I'll even erase this or take it back, because sometimes they are crazy with how they grade that. They don't like seeing 0 divided by 0. So if we want to do L'Hopital's, we have to evaluate. We have to write it separately. We have to say the limit as x is approaching pi over 2 of cosine squared of x. We say that that equals 0, and we say the limit as x approaches pi over 2 of sine of x minus 1 also equals 0. So we show the top and the bottom both equal 0, and that's indeterminate form. And then what we would say is by L'Hopital's, L'Hopital's, hopitals. Hopefully I'm spelling that right. By L'Hopital's rule, and then you're going to state that this limit right here. So I know it's a lot of rewriting, and I apologize. I just want to make sure you get full credit. The limit as cosine squared x over sine x minus 1 equals, and then you take the derivative of the top, and you take the derivative of the bottom. So we're going to say this is equal to the limit as x is approaching pi over 2. Now the derivative of cosine squared x, it's chain rule there, so that's equal to 2 cosine x, and then times the derivative of the inside is going to be negative sine of x, so that's the derivative of the top, divided by, and then the derivative of the bottom, the derivative of sine is cosine of x, and then minus 0, because derivative of negative 1 goes to 0. So that's what L'Hopital's rule states. It states that this limit right here that we started with is also equivalent to this limit here. That is using derivatives and limits, and it's just a new method to help us solve these. All right, so then what you do is you pretty much just start the whole problem over. You look at the limit we now have, and you see if you can solve this limit. And treat it just like its own separate problem. So we're going to see if we can solve it. Before I plug in pi over 2, it looks like I can actually simplify. I can actually cross out the cosines. So what I'm left with is the limit as x is approaching pi over 2 of 2, or negative 2, sine of x. And I can plug pi over 2 into that. I get negative 2 sine of pi over 2, which equals, it just looks like negative 2. So, I mean, I encourage you to even, graph this equation on Desmos, or even look at it, but you'll see that the limit is approaching negative 2. And we're able to solve that algebraically or mathematically using L'Hopital's. All right. Not too terrible. Let's keep going. Just see what we can get done. Okay. So we start by plugging it in. Start by seeing what we get. So if I plug 0 into this, that's e to the 0 is 1. Anything to the 0 is 1. Minus 0 minus 1 over the cosine of 0 is 1 minus 1. And we get 0 over 0. And again, sometimes I'll even erase that, okay? But that's just kind of my own scratch work to see if I got the indeterminate form. Remember how they like to see it. They want you to write it as separate limits, okay? If we ever get indeterminate form, so you're going to say, all right, well, that means that the limit is e to the x minus 1 equals 0. And the limit as x approaches 0 of cosine of x minus 1 also equals 0. So because the top and the bottom both equal 0, 0 divided by 0, that's indeterminate form. Then it's very procedural here. You're going to say by L'Hopital's, El Hospitals, El Hospitals. Yeah, it's definitely spelled weird. Then we're going to say by L'Hopital's rule, the limit as x is approaching 0 of e to the x minus 1 over cosine of x minus 1 equals the limit as x is approaching 0. And then we take the derivative of the top. So let's do that real quick. The derivative of e to the x is e to the x. The derivative of negative x is negative 1, and the derivative of 1 is 0 all over. The derivative of cosine is negative sine of x, and the derivative of 1 goes to 0. Okay? So now where we got that, we're going to plug 0 into the top and 0 into the bottom, and do this maybe in scratch work, but because we're trying to keep it very neat and looking good here, but I'll do it right here. If I plug 0 to this, I get 1 for e to the x, so that's e to 0 is 1, minus 1. And again, if I plug sine in 0 in for sine, I get 0. So this actually, again, is 0 divided by 0. So it turns out when I did L'Hopital's rule, I'm still in the indeterminate form. I get 0 over 0, which is no bueno. Okay? So the next step, again, is I need to state, I'm going to pretty much redo the whole process over again. I'm going to say, hey, the limit as x is approaching 0 of e to the x minus 1 equals 0, and the limit as x is approaching 0 of negative sine of x also equals 0. So then we're going to do L'Hopital's rule again and see if it works. Again, we're going to say by L'Hopital's, the limit as x approaches 0 of e to the x minus 1 over negative sine of x equals, and then we can just keep doing it. So we're going to take the derivative of the top. So we're going to say the limit as x approaches 0. L'Hopital says I can take the derivative of the top, and the derivative of e to the x minus 1 should just be e to the x. And on bottom, the derivative of sine of x, what's the derivative of sine of x would be negative cosine of x. And now if I take the 0 and plug it into that, that's e to the 0 is 1, and the cosine of 0 is also 1, so that's negative 1. And finally, my limit equals negative 1. So not the most terrible thing in the world, but we did have to do L'Hopital's twice. But just notice how we had to write it. We always have to show the top and the bottom limits separately. And if it's 0 divided by 0 or infinity divided by infinity, then we say by L'Hopital's, and we rewrite the equation. We say this equation becomes, and then we take the derivative of the top, derivative of the bottom. We simplify if we can. We plug in 0. We get the indeterminate form again. So then we repeat the entire process. Okay. All right. Let's keep going. All right. Example 3. So I'll plug 1 into it. So we plug 1, we get 1 squared plus 1 over 2 times 1 plus 1. And we get 2 over 3. That's not indeterminate form. Yay. Done. So sometimes when you plug it in and then you don't get indeterminate form. So there you go. In that case, it worked. It's not 0 over 0. Don't do anything extra that you don't need to do. All right, example 4. This is a fun one. I'm almost debating whether I want to save this for class or do it right now on the video. Yeah, I think I will. All right, let's okay, we're taking the limit to infinity. Let's consider what's going on here. So between ln of x and square root of x. If you think about their end behavior to infinity, ln of x and square root of x, hopefully we both know what those parent functions look like. But like as we go to infinity for both of them, they're going to infinity. And square and ln of x doesn't change that fact. If you graph both of them or even consider end behavior, this is going to end up being infinity over infinity. Okay, which again, I don't like to write that, but that's mostly scratch work. Erase it if you can. The point we're making is we show indeterminate form by saying the limit as x approaches infinity of the square root of x equals infinity, and the limit as x is approaching infinity of ln x quantity squared equals infinity. And because it's the same thing on top and bottom, because it's infinity divided by infinity, that's indeterminate form. So then what we say is we say by L'Hopital's rule. By L'Hopital's rule, the limit, it's a lot of rewriting here, the limit square root of x divided by ln of x squared equals. So then we take the derivative at the top, and we've taken the derivative of the square root of x a bunch, that's 1/2 x to the negative 1/2, and divided by, all right, let's take the derivative of ln of x squared. So power rule and chain rule, so we're going to have 2 ln of x, and then multiply by the derivative of the inside, and the derivative of ln of x is 1 over x. Okay. And I forgot to rewrite the limit part in front of that, but y'all be sure to do that. I forgot to write the limit part right about here, but that's okay. All right. Now, before we talk about what this limit looks like, maybe we should simplify it a little bit. This looks like a problem that we should definitely simplify. How about this top is the same thing as 1 over 2, say 2x to the 1/2 power. And on bottom, it looks like we have 2 ln of x divided by x. Now again, I'm trying to evaluate this limit to infinity. Let's keep simplifying it just a little bit here. And I might do this over in scratch work or whatever, but 1 over 2x to the 1/2 power. I'm going to do same change flip. Get something like that. And it looks like I can reduce x and x to the 1/2 power to being x to the 1/2 power on top. Or, yeah, x to the 1/2 power on top. So that's going to be x to the 1/2 power on top, and on bottom we got 2 times 2 is 4, so I should go ahead and just say 4 to simplify it. ln of x. Okay, so that was a little bit of scratch work. So what we're left with here, I'm going to pick back with where I left off, is that this limit is equal to the limit as x is approaching infinity of x to the 1/2 power over 4 ln of x. Okay, so if I plug infinity into this, well, again, it's the square root of x on top, so that is going to infinity. And on bottom, it's the ln of infinity again, times 4 doesn't change that. It's still going to infinity. So unfortunately, after simplifying it all down, it's still going to be an indeterminate form. So what I would like for us to do is not write it this way, but show it as the limit as x is approaching infinity of x to the 1/2, and say that that equals infinity, and say that the limit as x is approaching infinity of 4 ln of x also equals infinity. So when we show that indeterminate form, we're going to say by L'Hopital. By L'Hopital, the limit as x is approaching infinity, and the one that we're most familiar with right now is, or what we're dealing with, is x to the 1/2 over 4 ln of x. We're going to say that that is equal to, and I'm going to take the derivative of the top and the derivative of the bottom. So the derivative of the top is, again, 1/2. And I'm just going to go ahead, it's 1/2 x to the negative 1/2. So we'll just write that way. And on bottom, we got 4. And then the derivative of ln of x is 1/x. Okay. And I keep forgetting to write that limit part out in front, so please, I'll write that out front. But let's simplify that, and hopefully that's going to work out a little bit for us as well. So what this simplifies to is the limit as x approaches infinity. On top, I'm going to say 1/2x to the 1/2 power, and on bottom, I'm going to say 4/x. And then again, we can do same change flip here. I'm trying to write it a little bit neater than above. So that's 1/2x to the 1/2 times x over 4 if we do same change flip, which ends up equaling the limit as x approaches infinity. Again, we have x and x to the 1/2 power, which simplifies to x to the 1/2 power on top. And on bottom, we're left with 8. And then I plug infinity into that. The end behavior here is just straight up positive infinity. So after all that work, we figured out that the limit as x approaches infinity is indeed infinity. But we showed it algebraically, we showed it mathematically with L'Hopital's rule. But we had to do it twice here. And the simplifying in between was kind of the annoying part. But again, that's okay. We're at minute 26. I'll go ahead and stop it there. We got some really fun ones left over. Example 5, 6, and 7 I definitely want to do in class. So you're welcome to try those and maybe even look over the completed notes if you want. If we have time, maybe do 8, 9, and 10. 8, 9, and 10 are just practicing some of the same concepts again. But that's completely up to how the class is feeling about L'Hopital's by that point. And then we have some the homework here. And I try not to give too much homework this night, but to also give examples of a bunch of them. We're going to do an example of a function raised to a function tomorrow and how L'Hopital's applies to that. So like example 7. And we'll just kind of go from there. All right. Okay. Well, y'all are awesome. Y'all have a great day. And we got this.